Welcome to Module 205G on capacitor bank installations. We've already looked at capacitors and what they do when we went through theory, but now we're going to look at how do we install the capacitor banks inside our buildings. We have four objectives we need to cover with this module. First, we're going to talk about conductor sizing, then we're going to look at overcurrent protection, and then we're going to discuss what discharge circuits are and how to size them appropriately, and lastly, we're going to look at where to place the disconnecting means. Let's remind ourselves why we would have capacitor banks inside a building. Anytime that we have a commercial or industrial facility that has large inductive loads, such as motors, transformers, fluorescent lighting, or induction furnaces, it can create a very poor power factor for the building. So we would want to do what's called power factor correction. The easiest way to do power factor correction is to add in a capacitor bank, which would offset that inductive load. Some of the advantages that we'd see by correcting the power factor is that we would conserve our energy, it would reduce the load on the supply transformers for the building, it would also reduce the line current, which allows us to select smaller gauge wires. And it would also reduce the capital investment per kilowatt that the building has to have from the utilities. The first objective in this module is being able to properly select the conductors for our capacitor bank, but before we can get into that, we have to remind ourselves of what is happening with our capacitors. If you remember when we looked at DC theory on capacitance, we had what was called an inrush and a discharge current. The inrush current is when my capacitor is empty and I first start to charge it. What we saw was a flood of electrons coming onto the plates of the capacitor, which made for a very high spike of current that tapered off as the capacitor got charged. Also on discharge, we saw the exact same thing happen, just with the opposite polarity. As my capacitor is discharging, we have a sudden flood of electrons off the plates, creating a very high current spike again. This current spike is important because this affects how we calculate our ampacities for our conductors. In order to size the conductors, I had to look at Rule 26208 Subrule 1, which says the ampacity of the capacitor feeder circuits and branch circuits shall be not less than 135% of the rated current of the capacitor, and that's to allow for that inrush and discharge current. If, for example, I had a capacitor bank that was rated at 40 amps, I would have to take that 40 amps of rated current, multiply it by 1.35 to allow for my inrush current, and I get a value of 54 amps. This is the minimum ampacity my conductors must safely be able to carry. And of course, now I just need to go over to table number 2, and I would find that I would require to have a number 6 rated 65 amps at 75-degree termination temperature. Of course, your termination temperature is going to depend on the equipment that you're using, but make sure you're using the correct column in the table. When it comes to the feeder wires for multiple capacitor banks, I still have to apply this 135% rule. So if I have 3 capacitor banks, each rated at 40 amps, I have a total accumulated ampacity of 120 amps. I take this 120 amps, multiply it by 1.35 to get a value of 162 amps, which is now the minimum ampacity of my feeder conductors. And now I go to table 2 and I select a 2-odd wire. This calculation works for my feeder conductors and all my conductors coming up to that line. However, I need to consider a couple different things when I look at the tap conductors coming off those feeders to feed the individual capacitor banks. When it comes to the tap conductors for the individual capacitor banks, I have an either-or situation that I need to consider. The either-or situation is written down in 26208, where I look at Subrule 1 that says they have to be at least 135% of the capacitor ampacity. So that means each of these capacitor banks must be fed by a conductor no smaller than 54 amps. And if I look at 26208 Subrule 2b, it says the conductors complying with Subrule 1 and also have an ampacity not less than 1/3 of the branch circuit conductors from which they are supplied. So I have to look at the ampacity of my feeder conductors, that 2-odd conductor that I had, which is rated at 175 amps. And my tap conductors cannot be any less than 1/3 of the ampacity of that wire. So now here's my either or. I have to compare the 1/3 of my feeder conductors to the 135% of the capacitor ampacity, and I choose the larger one of the two. In this case, it's going to be the 58.3 amps I have as 1/3 of my feeder conductor. And I go to table 2 and I find that I need to use a number 6 gauge wire. Make sure you're reading through that rule 26208 and you understand how to separate subrule 1 and subrule 2 and figure out what we are required to have for tap conductors. If the capacitor bank that you're dealing with does not have a rated ampacity, which can happen, it will have either a rated VAR rating or a Farad rating on it somewhere. And if this is the case, we need to rely on our theory formulas in order to calculate what we need. Remember that if I have the capacitance, I can figure out what the capacitive reactance is and I can use that to calculate the current. Or if I'm given the VAR value, I can also use that in order to figure out my current as well. Make sure that you're familiar with these capacitor formulas and you know how to use them in order to find your current. And then make sure that you are aware of how to use that current rating in order to calculate your conductor size. You've reached the end of 205G Part 1 on conductor sizing, so make sure you review this until you understand the concepts within this video, and then you can continue on to Part 2.